We are going to look at an example of using a table, a graph, and an equation to represent a linear equation in a word problem. The cost to take a taxi is a fixed cost of $15 plus added on is $1.50 for each kilometer the passenger travels. What you'll notice is that this question talks about the distance traveled and the cost of taking the taxi. These are going to be the independent and the dependent variable in our word problem. The distance traveled D is going to be the independent variable X, and the total charge for the ride C is going to be the dependent variable Y. The amount that you're charged for the taxi ride depends on how far you've gone. The rate of change and the initial value can be found in the word problem. The two numbers that you see there are going to be the two values that we're going to use in our equation. When given a description in words, the initial value will be the fixed cost or the starting or beginning value. In our scenario, the customer must pay an initial fee of $15. Even if they travel 0 kilometers, they must pay $15. To find the rate of change, look for words such as per or for each to help you. Remember that a rate of change is just a unit rate like we looked at before. How much for 1 kilometer, 1 item, 1 second, etc.? Here the rate of change is $1.50 for every kilometer, or $1.50 per kilometer. Let's put these two values into the equation. The linear relationship is always represented by an equation that looks like this. Using our new variables, C and D, we have an equation C equals blank D plus blank, where we need to fill in those blanks. The rate of change is multiplied by the independent variable. So in this scenario, $1.50 per kilometer is multiplied by the number of kilometers the passenger travels. So $1.50 goes in the first blank, and we need to add on the initial value of 15. So if the traveler gets in the taxi but travels 0 kilometers, $1.50 times 0 is just 0, plus 15 gives us that initial fee of $15 that we pay no matter what. If we use a table to represent this word problem, the first thing we need to do is to make two columns. D, the distance traveled, was our independent variable, so it's going to go in our first column. And C, the dependent variable, our total charge for the ride, is going to go in the second column. And I'll explain to you in just a moment what the third column is all about. I have selected to go up by 5 kilometers each time in the distance column. The reason I did that was I wanted to pick numbers that had a consistent difference between them. So I didn't want to skip from 0 to 10 and then maybe to 100 because it's going to be harder to see the pattern. I also didn't want to go up by 1 kilometer each time because that would make for a very short taxi ride. The cost is going to depend on the distance traveled. So I can use my equation that I just saw. Cost equals $1.50 times D plus $15 to help me fill in the table. I change the distance to whatever the distance is in the first column. I multiply it by $1.50 and then I add 15. If, for example, I wanted to find the cost of a 10-kilometer taxi ride, I would take 10 and multiply it by $1.50, which gives me $15. And then I would have to take 15 and add on the initial value of 15 to get 30. So you could do this to fill in your chart for as many values as you wanted. The initial value, or the fixed cost of $15, happens when the distance traveled is 0 kilometers. So this is a very important entry in my table. When the independent variable is set equal to 0, the dependent variable is going to be the initial value. The rate of change we discussed on the previous slide is $1.50 per kilometer. If the rate of change is $1.50 for 1 kilometer, we want to know how much is it going to cost for 5 kilometers of travel. So we're just going to take $1.50 and multiply it by 5 to figure out how much do we need to add for each additional 5 kilometers that we travel. And $1.50 times 5 gives us $7.50 for 5 kilometers. Now we're going to calculate the finite differences and put those into the last column in our table. The finite differences are found by subtracting the y value above from the y value below in the table. So we're going to take the second y value, 22.50, and subtract the first y value, 15, to get $7.50. And we're going to continue this down the column. So $30 subtract $22.50 is going to give us $7.50. $37.50 minus 30 is going to give us $7.50. And 45 minus $37.50 is going to give us $7.50. So if we go through this process of finding the finite differences and they're all the same, this means that we have a linear relationship because the y values are changing by the same amount each time, and the x values are also changing by the same amount each time. What you'll notice here is that the $7.50 that we got for the finite difference in the table matched up with the rate of change calculation that we did over to the side here. On a graph, you'll notice a lot of the same information that we saw in the table. The first really interesting point that we always want to make a note of is the initial value. The initial value, when the distance traveled or the independent variable is set equal to 0, is 15. This corresponds to the point 0, 15 on the graph, or the vertical intercept. So it's the starting point for our graph. Each time we travel 5 kilometers, we pay an additional $7.50. So if I draw a rate triangle between these 2 points, we'll notice that there's a change of $7.50 for 5 kilometers traveled. This is our rate of change triangle that helps us find the rate of change from the graph. So the rate of change on our graph is the rise, $7.50, over the run, which is 5 kilometers. And this takes us back to our rate of change from our equation, $1.50 per kilometer.